Hey, good afternoon. Welcome back. Hope you had a good spring break and all rested, unlike me. Important administrative announcement. This Saturday is the CS61A dim sum brunch. This is a tradition that started too long years ago when during the adventure game project somebody said, "What's a pot sticker?" So we decided that an important educational experience was dim sum. For those who don't know about it, they come around with trays with little teeny plates with, 2 or 3 or 4 tidbits, and you say, "I want some of this and some of this and some of this." And in real traditional old-fashioned Chinese dim sum places, they just count up the plates on your table at the end to write you a bill. But in modern American, we don't trust anybody dim sum places, they make note as you're going along of how much you ate. So that's how dim sum works. I have to say it's not very vegetarian friendly or kosher friendly or halal friendly. That is to say, there's lots of ground up mystery meat that turns out to include pork and shrimp. But it is delicious. And no, we're not treating. Should plan to spend $10 to $15. And we're going to meet up outside the Berkeley BART Saturday morning. I know this seems ridiculously early to you, but if you wait until noon, it takes hours to get in, especially with big groups. So you either meet us at the Berkeley BART at 10:30, or else meet us at Legendary Palace in Oakland at 11. I would tell you all about how to find Legendary Palace, but you all have computers, so shouldn't be necessary. You can do the same Google that I did. Okay. This week we're talking about 2 related topics. Today we're looking at another programming paradigm called client-server. So the way the course is structured, there are 2 paradigms that we look at length. We've done that. They are functional and object-oriented programming. And there's 2 more that we barely touch on. So when you come out of the course and you've forgotten the details, you should know that this exists, and you should understand sort of the big ideas of each paradigm. And we'll talk in a minute about the big ideas of the client-server programming paradigm, which is very, very important in computer applications today, where you connect to Facebook, and you have a client on your computer, and they have a server on their computer, and you talk to each other. So instead of the computation happening in one place, it's sort of distributed over a network. Okay. And later in the week, we're going to be talking about concurrency, that is different things happening in parallel, and how that gives rise to programming predicaments that it's really best if you understand ahead of time, because once you introduce a concurrency bug in your program, you're never going to find it. You can ask anybody who's taken 162 about this, about all the all-nighters that they've pulled in labs because of concurrency bugs. So you really want to understand that. And they go together because when you have a server that's supporting many, many clients at once, you're doing concurrency. And so this kind of problem arises a lot in this particular way of organizing a program. Okay, so I have 2 windows open. I'm connected to star.cs. And in principle, you can connect to the server that I'm about to start up from anywhere on the internet, but in practice, the instructional computing folks have a firewall that prevents connections from anywhere else. So if you want to play along, you have to SSH to star. So I'm going to say over here, I am server start. And it's going to tell me 2 magic numbers. It's going to tell me my IP address, which is 128.32.42.27, and it's going to tell me a port number, which is 42275. Okay, so those of you who have laptops, if you SSH into star and load 61a/lib/ twiddlecs61a/lib/ im IM for instant message, something you all know about. When you say IM enroll, that's an E, you have to give your host in quotation marks. And that's because it has digits and decimal points, so it looks like a number, but it's a badly formed number because it has more than one decimal point. So we have to tell Scheme to treat it as a character string by putting it inside double quotation marks. So 128.32.42.27 is the internet address of star.exe, the instructional server on which we work in the lab. 42275 is just an arbitrary number that the operating system picked for our use as a port number. Good, there's somebody. Here, let me sign on my other window. So I can say, oops, stop that. I am enroll 128.32.42.27, close quote, 42275. This one isn't in quotation marks because it's just an integer. Interesting. Okay. I wonder who this person is whose name is supposed to be Brian Harvey. That's not me. This is me. Okay, so we're already seeing some security problems in this protocol. But that's OK. I can say I am, quote, CS61A TE. Hi, welcome to instant messaging. It says OK, and on his screen it should pop up a message. And over in my other window, we can see all the messages going back and forth. Yeah. Right. Oops. Okay. So here's the message that I got. Interesting. So unlike real IM software, this version is instrumented with a lot of extra debugging printouts. So you see a lot of junk scroll up on the screen about, I got this message and I'm doing this. And that's so that when you're working on it in the lab, which you will be this week, you'll have an easier time of debugging what you do. Ping. OK. I am, quote, CS61A-SE, quote, Pong. All right. OK. So this is the program that we're looking at today as an example of client-server programming. I'm going to just, whoops, not maximize. I didn't mean that. I meant minimize. Just to be a little less interesting. And so that I can pop up, hello? in another terminal, and look at the code. Okay, so first of all, probably most of you are already familiar with all this, but just a brief detour into how the internet works. This is not a class about how the internet works. There is one of those. It's EE122. But 128.32.42.27, that's just a 32-bit number divided into 4 pieces of 8 bits each. They thought it would be easier to remember and type internet addresses if they put in those dots. Everything that's 128.32 dot something is a computer in the EECS department at Berkeley. So we own 128.32, which is 2 to the 16th addresses. 2 to the 16th is 65,000 and some odd. So that's a block of 65,000 addresses that we own. And we have some other ones, too. The entire internet address space, using this protocol, is 2 to the 32nd addresses, which is about 4 billion. We are running out, not because there are 4 billion computers on the internet. There aren't, but because big chunks are allocated a chunk at a time, and they're not all full. So we may not have 65,000 computers in our bit of address space. Maybe we only have 20,000 computers, in which case that's 45,000 unused addresses that nobody else can have because, you know, they belong to us. And the theory is that sooner or later we will have 65,000 computers because, you know, each little dust speck computer that the remote sensing people build is going to have its own IP address. There's a solution to this problem called IPv6 that has 64-bit addresses instead of 32-bit. I don't remember how much 2 to the 64th is, but it's more than the number of atoms in the universe, I think. I think that's right. So we're not likely to use those up anytime soon until we start exploring parallel universes. 42275, that's just a number that nobody has to know except the client and the server. So what happens is when you say IM enroll in Scheme, your computer sends a message to star.exe saying, I want to connect to port 42275. And the operating system on star looks up which application program has registered that port number and connects your incoming request to that program, which in our case is the IM server. So you connect to the IM server by knowing its port number. You know its port number because I wrote it down on the board and you copied it. In general, the way real systems work is that there is an assigned port number for a certain kind of service, and everybody just knows, or rather everybody's computer just knows what that port is. So if you want to make an HTTP connection, that's port 80. If you want to make a telnet connection, which nobody does anymore, that's port 22. Those are the only ones I have memorized. But you don't have to have them memorized because the software that runs on your computer has them memorized. So when you run Firefox or something and you type in a web address, it knows to connect to port 80. Unless the web address starts HTTPS, which stands for Secure HTTP, which has a different port number, which I forget, but somebody knows. So those are low numbers, like, you know, 2-digit numbers for these well-known ports. The higher numbers are reserved for private or experimental protocols like our IM thing. So that's a private protocol. If we wanted to make $1 million by distributing our instant messaging software, competing with AOL and Yahoo and those guys, we would make a request for a registered port number. We would make that request to ICANN, I guess, which is the Internet Consortium on Assigned Names and Numbers. And they would give us a number that thereafter everybody would know. And, well, we would distribute free client software that would have that port number built into it. And, of course, our servers would know what the number was. OK, so that's host addresses and port numbers. So what happens when you enroll? You send a message. Well, let's start actually right at the beginning. Here's IM server start. This is how I started up the server. So what does it do? It prints a message. It calls make server socket. A socket isn't a number like 42275. It's an abstract data type. It includes a port number and a bunch of other things. So make server socket, that gives us a socket, which is an abstract two-way internet connection, or a kind of repository for connection. We're not connected to anybody yet. People are going to connect to us on it. And now we print server IP address and server port. We get the IP address from the operating system. And right here, socket port number is a selector for sockets that gives us the number 42275. OK? Now, do I expect you to memorize all these details about what a socket looks like and everything? No, absolutely not. None of those details are important for you to remember. It's important for us to walk through it, for you to get a sense of how it works. But don't remember the details. If you actually are interested in the details of networking in SDK, in my lecture notes, pages 332 to 334 in my copy, are 3 pages of documentation of SDK networking primitives. Again, none of this is stuff you have to know. It's only there in case you're interested and you want to play around with it. OK. Now comes our first example of the most important idea that we're going to talk about today. So if you've been things going in one ear, out the other, listen up. When socket ready is a networking primitive in SDK that takes 2 arguments. The first one is a socket. So we asked for a socket, we got one, and now we're using it in this when socket ready. And the second one, the big important idea, so important that I'm going to write it down, if I could only find, there you go, is a callback procedure. So when socket ready doesn't sit there stuck until somebody connects to the socket. When socket ready returns instantly. But it has established a matching up between our server socket and this procedure. OK? This is a procedure of no arguments. And the operating system is going to poke STK when a connection request comes in for port number 42275. The operating system is going to look up port 42275. It's going to find this socket. It's going to find the user process associated with that socket, and it's going to wake up that process and say, hey, do this. And STK represents the do this in the form of a procedure, unsurprisingly. In those other languages, you can't generate procedures on the fly the way this lambda is doing. But what they do is they have something called a pointer to procedure. So if you've written a procedure ahead of time, you can use that written ahead of time procedure as an argument to something. And that's how they do callbacks in those other languages. But in this case, for example, you'll notice that the procedure that is now highlighted includes within it a reference to server socket, which is a local variable. It's just inside this procedure because it was created. Oh, no, I'm wrong. It's a global variable. I lied. But it could have been a local variable, in which case this lambda would still have access to it. We'll find some things like that later on. So forget I said that for now. But the important part is this is a callback procedure. What that means, a callback procedure, is a procedure that the system, this is a kind of hand-wavy thing, the system, something that somebody else wrote, not you, is going to invoke when a certain event occurs. In this case, the event is socket ready, meaning somebody requests to connect on this socket. Okay? So what does this procedure do, this lambda? Well, it prints a message, new client connecting, and then it does this interesting thing. It says, make me a copy of that socket. What's that for? Well, many different clients are going to connect to this server at once. And each client is going to have its own socket, so we can keep them apart, pull them apart, right? So if two messages come in right at once, it doesn't matter, because one message will go to one socket and one message will go to the other socket. So socket dupe is an SDK primitive that says make a copy of the socket. So now we have a special socket just for this client who's connecting right now. And then we call handshake, which I'm going to look at in just a second. OK, questions about what a callback is? All right. Who's programmed with callbacks before in some context? Hardly anybody. OK. A few people have. This is a very, very, very ubiquitous concept. It's not just for writing network servers. So for example, if you're writing a program that has a user interface that has a window, and in the window there are buttons you can click with your mouse, and there's little rectangles in which you can type text and all of that stuff, associated with that window are probably a bunch of callbacks, one for mouse clicked, one for key press. And if it really wants to get fancy, your program can have a callback for key down and another callback for key up. And that's important if your user interface lets people type, you know, Control, Alt, Shift, blah, blah, blah. You can keep track of all those modifier keys that way. So all of those things work with callbacks. So a typical program that you see that you buy in the store, you start it up. It takes a while. It sits there with that splash screen, you know, saying this is a great program, send money, you know, and then the real window pops up. And then after that, the program does nothing. It's sitting there doing nothing, waiting for a callback that could be from a bunch of sources. It could be something you do, like click the mouse or type some text, or it could be on a network connection, or it could be some input-output on your local disk finishes or something like that. So there are many, many ways that things happen. All of it is done with callbacks. And what your program is doing is just sitting there saying, I'm going to sit here and wait until I get a callback about something. All right, so let's find handshake. Here it is. It has a lot of comments, which I'm going to skip over. What we're about to do, the procedure is called handshake because what it's about to do is something called a three-way handshake. I send a message from the server to the client. Then the client sends a message to the server. Nope, I have it backwards. The client sends a message to the server. Server sends a message back to the client. Client sends another message back to the server. So how does this work? We say let port from client be socket input of SOC, and port to client be socket output from SOC. So here, a port is like half of a socket. It's a one-directional connection between us and the person on the other computer. And get request, that's not an STK primitive. It's something that's part of this IM package that waits for a connection and says, OK, let me find the data and parse it into pieces. And then comes something interesting. It says, if request is false, that's what not rec means, then shut down the socket. Otherwise, do some other stuff. So what you're going to see is that there's a lot of error checking in this code. Mostly, the procedures we've written so far, the whole first half of the semester, are written on the assumption that nothing's going to go wrong. I mean, not that the user can't make a mistake, but that the hardware is going to work. That's an assumption you can't make in networking. Network connections fail for all kinds of reasons. Maybe the other computer that you're talking to crashes. Or maybe in between you and that other computer, there's somebody in the middle that your connection is going through that crashes. And maybe you can root around that, and maybe you can't, depending. So network connections are really, really flaky. And network code always does a lot of checking to make sure we're still connected. OK, so print the message. And now messages have different parts. There's an action, there's a sender, there's a receiver, and there's the text of the message. So here we're looking to see if the action part of the request is the word hello. So what we're expecting is that the client is going to send hello to the server. If it sends anything else, we give an error message and shut down the socket and go away. Because it's a client for some other system, not ours. If that works, then we look at the source of the request. Who is making this request? CS61A-XY. And we look to see if that person is already included as one of our clients. If so, then we send a request saying sorry and shut down the connection. Because you can't have the same name as a client twice on two different computers, two different clients. So let's say we get past that test. So it's a hello message from someone we haven't seen before. Then we still make sure of one more thing. Oh, no, we don't. I'm sorry. Then we send a request. Make request is a constructor for an abstract data type. And the source is the word server. So it's a message from the server. And then the destination of this message is whoever is trying to connect to us. The action that we're saying is welcome. and there is no text. There's just the action. So we got hello. We send back welcome, and send request returns a value, basically true or false, meaning did that work or not. If it didn't work, shut down the socket. Okay, now we wait for another message to come in. So we get request, client fork. If we don't get one, shut down the socket. Otherwise, we make sure that this new message from the client has an action of thanks. So client sends hello, server sends welcome, client says thanks. One of your homework questions this week is, why do we have to do a three-way handshake? Why isn't it good enough to just send one message each way? Why do we need two messages from the client? So you can work that out. And then finally, that all worked. So now we call register client, which just puts the client in a list. So we associate the name, CS61A- whoever it is, with the socket corresponding to that person. And that's done. That's it. And we return OK. Whew. All right, now, let's look at register client, which is right here. How do we do that? Well, we add client to table. And then we call setup client request handler name socket. So let's look at setup client request handler. This is all part of what happens when you IM enroll. This is what the server is doing on your behalf. So here's setup client request handler name client socket. This is an internal define of a procedure called client request handler. Takes no arguments. So it says get the input port, get the output port, get the request. If there is no request, forget it. Otherwise, received request. And there are two messages. This is like a dispatch procedure in object-oriented programming. These requests, there are two different actions we know how to do. And the first one is send message. In which case, we look up the port for the person you're trying to talk to, and then right here, we do send request from the source to the destination, receive message, and then request data, which is whatever the text is that you're trying to send. So we send a request over the network to the client, and the action of that part of that request is receive message. The other possibility is that the action is logout. So one is send message, and the other is logout. If it's logout, then we just remove this person from the database. Otherwise, it's an unrecognized action, and we sent back a message saying, I don't know how to do that. You sent a request that, isn't either logout or send message. And that's the end of that internal definition. And now, here's the actual body of setup client request handler. It says, when port readable. So this is another callback situation. So which port? Socket input of client sock. And what's the procedure, the callback procedure? It's client request handler. So this whole thing could have been a Lambda expression. The reason they did it as an internal define is just that there's a lot of code in that thing, and if it started 2/3 of the way across the screen with a Lambda, it wouldn't be very readable. So client and server callbacks. The client also has a bunch of callbacks. So let me bring these windows back. Oops. Wait. Okay. So here I am. And I'm enrolled as a client. And meanwhile, I can do computations in STK. Right? I can do anything I want in STK and also receive messages at the same time. How come STK can do both of those things at once? Because of something called threads. Threads used to be called lightweight processes. Just kind of a good name because it explains the idea. A process is something that your computer is doing. It's some program that's running on your computer. A thread is like a process that shares memory with other processes. So you start up a program, and that program can spawn off various threads to do different things. So in the server, back here, nope, back here, when we said, way back at the beginning, well, also for this when port readable, when we say when port readable, that returns right away. And we can go on and do other computations. When the port is readable, when a new request comes in, the system will start a new thread and invoke the callback procedure in that new thread. So it shares all the program's global variables and everything, but it's a separate computation from the main SDK read eval print loop. The server is going to have many, many, many threads, one for each client, plus one for the read eval print loop. Because I can do that same trick in the server. I can type in scheme expressions and get values back while this is running, because we set up a special thread for each task. Okay? So that's the other part of this client-server paradigm. So second big idea. Okay? If you understand what a callback is, and you understand what a thread is, that's pretty much what I would like you to understand about the client-server paradigm. And understanding what a thread is means understanding that several different things are happening in parallel that share access to global data among all the different threads. That's going to be important next time when we talk about what can go wrong when different threads share the same data. Okay, what have I forgotten to say? All right, let me give you the 5-minute story about how the internet works. Okay, so the internet hardware provides the ability to send unreliable packets to the local network. Okay? What that means is your computer is connected to a network. Like right now, your computers are probably all connected to Air Bears. Okay? So your internet hardware basically knows how to send messages to only one place, which is the airbear's server that's running in this room. And furthermore, the messages may not always get there. So that's not so good. Oh, what's a packet? A packet is just a bunch of information, but just one bunch. There's no idea of a continuous stream of information back and forth. It's more like tossing a ball than like having a phone conversation. Okay? So on top of that, we have the Internet Protocol, otherwise known as IP. And what that does is it provides an address for every computer in the world, and it provides a mechanism for messages to be forwarded from one computer to another. By the way, this is a very, very remarkable thing, that everybody in the world who has a computer, well, everybody in the world who has a computer that's sort of in the middle of things on the network, not you. You mostly don't have to forward messages because you're at the very end of a thread that, that only connects to one other place. But everybody who has a computer that's connected to a bunch of places takes messages from just anybody, could be a competing company, and passes them along and doesn't read them. At least we hope so. There's some evidence that commercial ISPs actually do read your messages as they go from your computer into the network in order to sell information about you to advertisers, but that's a whole different subject. But this system just sort of grew organically, that everybody cooperated with everybody when it came to making the network work. And it's quite a remarkable example of large-scale human cooperation. Doubly remarkable these days when we have the idea very prevalent in society that nobody ever does anything nice for anybody unless they get paid for it. And that really was not the case in the building of the net. Okay, so the Internet Protocol gives us the ability to send unreliable packets worldwide. So IP has not solved the reliability problem. All it's done is extended your reach from people right around you to the world. For some purposes, that's good enough. I send a message to an internet time server saying, what time is it? Right, which your computer does periodically. If that message doesn't get there, so what? You just try again. Okay, it's no big deal. But if you're trying to if you're trying to send a file, a big file over the net, it gets divided up into little chunks, and if some of the little chunks get there and some don't, that's not so good. So now we have the transmission, right, control protocol, TCP. And what that does is it gives you two-way continuous ordered reliable streams. Okay, so built on top of unreliable packets, we now have well, it isn't 100% reliable. If the computer you're talking to crashes, then, what can we do? But if some computer in the middle crashes, TCP will work around it. So it'll try again. It'll keep trying until it gets through. And furthermore, it puts a serial number on each little packet so that the receiving end makes sure they come in order. It does a lot of very complicated stuff. TCP is very hard to get right. If you just read the specification and implement it, you will end up with code that runs way too slowly to be used. And so there's a whole science of coming up with wrinkles to TCP to make it run fast enough. And then, on top of that, we have an application that gives you, whatever it gives you, a web browser or a file transfer protocol or something. So this is called the network stack. In the literature, somebody a long time ago came up with a 7-layer stack. This is a 3-layer stack, 1, 2, 3, really. Well, 4 if you count the application layer. And this is called TCP/IP, which is an abbreviation you've probably seen. This is what it stands for. All of this goes on behind the scenes in your computer. Hardware, there's lots of different ways of building networking hardware depending on what problem you're trying to solve. So right now, you are all using Wi-Fi connection, which is a radio-based way of communicating with a server. But maybe at home in the dorm, if you live in a dorm, there's an Ethernet port you can plug into, right? In the newer dorms anyway. So you can plug a cable in and get onto the internet that way. The Ethernet is a bus, a collection of wires that sort of runs around in one local place. And that hardware has its own protocols associated with it. So one of the Ethernet issues, my favorite example about this, is what happens if 2 people try to send a message over the local Ethernet at the same time? Well, the answer is they kind of mix up with each other and get garbled. And so everybody on your local net reads this and says, uh-oh, this is a garbled transmission, and drops it. And in particular, the computers that were trying to send a message can see their own message as it comes back. And they say, uh-oh, that didn't work. And then each computer waits a random amount of time and then sends it again. The random amount of time is important because it makes it likely that next time the 2 computers won't collide when they're sending this message. If it just kept trying, boom, 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 then they would keep on colliding over and over again, and the message would never get through. So this is the kind of thing that people think about at the hardware level. Higher up in software, we think about things like how much redundancy do we need in order to get this illusion of reliability in the connection? How do we make sure things come in the right order and so on? OK, you're going to play with this in the lab. There's both lab exercises, and some of this week's homework is about it. And then we'll talk about concurrency on Wednesday.